Okay, so what we want to talk about is why muscle architecture is important. So if we look at this two pictures here, we can see this is a picture of the back, the superficial muscles, and we can see the trapezius here. We can see the muscle fibers attached to the tendon along the spine and up here in the neck, and then run really full length to their insertions. So the muscle fibers are uninterrupted and fairly long, especially here in the lower trap. If we compare that to the infraspinatus muscle, which is deep to these superficial muscles here to the left, we can see that here's the humeral head and humerus. This is spine of the scapula here, and this is the infraspinatus here, labeled ISP. We can see the muscle fibers are really running into this central tendon here that forms part of the rotator cuff. And so these muscle fibers are relatively short and they're running at an angle, especially here distally as they go to attach into the rotator cuff. And so they're much shorter and they have a very different arrangement. And as we go through the body, you're going to notice, as you do the dissections in the body, you're going to notice that these fiber directions are very different relative to their tendon origin insertion as you study anatomy. So our questions are, why do muscles look different? What effects does a muscle's fiber arrangement or organization have on its contraction profile? And the key concepts are sarcomeres in parallel versus series, physiologic cross-sectional area, and how that relates to Panasian angle, and the influence of all of these factors on a muscle, whole muscle. So force velocity and force length characteristics with special attention to its peak velocities of contraction, especially relative to shortening, and peak force output. Okay, so let's start by talking about muscle fibers in parallel versus series. So what we're going to do to get this going is to focus, instead of on muscle fibers, let's speak about the smallest contractile unit, which is a sarcomere. So what does it mean to have two sarcomeres in parallel? How does that affect some of the characteristics of a muscle? And in particular, let's look at the peak contraction velocity and then the peak force and the total amount of change in length a muscle can achieve. So if we have two sarcomeres in parallel, what does that mean exactly? So let's have sarcomere 1, Z-band here, another Z-band here. Then we have sarcomere 2 that we're going to put next to it. So it's in, and we're going to say this is our parallel arrangement. And then let's contrast that with if we took these two sarcomeres and put them in series. So series would be taking sarcomere 1, there's Z-band, and then there's the sarcomere, and then instead of putting it next to it, we put it in line with it. So sarcomere 2 then would be here. Okay, so how does this arrangement, parallel versus series, affect these key muscle variables? So let's do parallel first. So if we think about force, we have the force in this case, the force in sarcomere 1 plus the force in sarcomere 2 equals the muscle's total capacity. So this is peak force here. Okay, if we look at series, this muscle, we take the sarcomeres if they're in series, well, what happens here is now we have the force in S1, sarcomere 1, it's going to equal the force in S2 because essentially the force is being transmitted to the bone, so they don't sum or add, they're both contracting the same amount and they're transferring that force to the bone. So this is going to equal their force peak. Okay, and we'll label this series and parallel, and it's obvious that in this case the peak force is 2 times that for the parallel muscle as compared to the series. So quite a large or significant advantage for muscle fibers when they're in parallel. Okay, so that covers this. So now let's look at how this might affect peak length, and then we'll relate that to velocity. So essentially here, when fibers are in parallel, how does that affect change in length? So we can see that if this muscle shortens and this sarcomere shortens and this sarcomere shortens, the overall change in length of the muscle really is not going to change that much because they're in parallel. So we have the change in length of sarcomere 1 is going to equal the change in length of sarcomere 2, and so that would be equal to the overall change in length of the muscle. They're not summing, they're just all the same. So, but here we can see it's much different, right? So they are going to sum, and the overall change in length of this muscle is going to be more. So we have the change in length of sarcomere 1 is going to add to the change in length of sarcomere 2, and so the overall change in length of the muscle here will be, in series, is going to be much larger than the muscles, fibers, or sarcomeres that are in parallel. So then how does this relate to contraction velocity or peak shortening velocity? If we take the same change in time and we divide both sides by the same time increment, we can see that what's going to happen is, because velocity is the change in length over the same time interval, that the peak contraction velocities are going to be much higher for the muscle with more sarcomeres in series. Okay, so now let's look at the effect of Panasian angle and what that means for physiologic cross-sectional area. In the process of doing that, we'll define physiologic cross-sectional area. So if we look at different kinds of muscles, and they're represented here, and I tried to kind of draw the same basic muscle just with different muscle fiber arrangements, and they get named different things like strap, and there's different names for these muscles that have fibers that kind of run the full length from tendon to tendon, or like a pennate muscle that stands for feathered, where the muscle fibers are angled relative to the line of pull of the muscle. And then if it has many pennate arrangements, it might be bipennate or multipennate, when the fibers are both coming together into this single tendon. Okay, so we want to think about the effect of this angling of the muscle fibers, because it happens in many different muscles in the body. So first let's define it, and this angling is called Panasian angle. So here we have the angle of pull of the muscle fibers relative to the length of the muscle, so we'll call it theta, and in this case it's 0, and so this is, the muscles simply just are in line with the origin insertion of the muscle. And here, if we look at this pennate muscle, what's happening is the muscle fibers, if we kind of represent the line of pull of the muscle as this black line, they're at an angle here with the line of pull of the muscle. Then we could do it again here for this. So each of the fibers has this kind of angle going on. Okay, so we want to ask, what's the effect of this? Well, this is the muscle fiber. Each individual muscle fiber is pulling at this angle relative to the tendon. We could write this out as the force of the muscle fiber. Well, we could calculate how much of this force is actually pulling on the tendon, and because some of it's pulling parallel to the bone, right? And so that's actually lost. So the total tendon force equals the force by the muscle fiber cosine theta. And so there's a reduction in the contribution of that muscle fiber to the pull of the muscle. Well, that should immediately make us think, well, that's not optimal. Why aren't all muscles arranged like this strap muscle? And if we think even a little bit more, we could see that, okay, the Panasian angles tend to be pretty low. So, a Panasian angle muscle a lot of times is like 10 to 30 degrees. But if we take a bipennate or multipennate muscle, the Panasian angles can be quite high. They can reach up to 30 to 60 degrees. And so the more the angle, well, the less the force that's actually being realized at the tendon level. So it seems very inefficient. And so how can this be an advantage? Because the body is certainly taking advantage of it for some reason, right? So let's then now change the topic to cross-sectional area and relate this to fibers or sarcomeres in parallel. So if we take the strap muscle here and we look at its cross-sectional area, we could kind of imagine drawing the cross-sectional area like this, and this would be equivalent to the cross-sectional area of that muscle, and this would be essentially give you a measure of how many sarcomeres are in parallel. So we could put sarcomeres in parallel, and then that would be directly proportional to the peak force of that muscle. And so this is a key characteristic, right, of a muscle, right? So we could say, okay, well, we can look at that cross-sectional area and know that force capacity when we're just looking at it anatomically. Well, what happens here, though, if we look at this and we did the cross-sectional area like this, is that really the perpendicular output of those muscle fibers? Not really. Its cross-sectional area has got to be perpendicular to these muscle fibers, and so if we want to go perpendicular, we have to draw it like this. And I'm like, okay, that's interesting, right? Because basically what's happened is this cross-sectional area we're going to call physiologic cross-sectional area, and physiologic cross-sectional area simply takes into account Panasian angle. So it gives you the cross-sectional area perpendicular to the Panasian angle. So what this is telling us is that for this particular muscle, the fibers in parallel are represented by the physiologic cross-sectional area, this kind of angled cross-section. And so this is much larger than the cross-sectional area that we see here that's perpendicular to the line of pull of the muscle. And so as long as the Panasian angle is not too bad, you get the benefit of having the sarcomeres in parallel outweighs the small loss in force due to the fibers not being directly aligned with the muscle. So what we can see here, though, is like now we're saying, well, in a bipennate case, or a multipennate case, what's happening? Well, the strategy of the muscle here is just to get a lot of muscle fibers in parallel. And so even though the Panasian angles may be higher, we can't really simply draw a PCSA like this because we have to be perpendicular to every single muscle fiber. And so in this particular case, what's happening is the strategy is to use the Panasian angles and the multipennate arrangement to create a lot of muscle fibers in parallel. So the PCSA of this muscle in the bipennate case is going to be larger than the PCSA of a pennate muscle and much larger than the PCSA of a strap muscle. All right. So what's happening is the Panasian angle is occurring and there's some loss of efficiency there, but the PCSA, or the ability to put muscle fibers or sarcomeres in parallel, is outweighing the inefficiency of having a Panasian angle. Okay, so what's the consequence of this, though? So we could see, well, this bipennate or multipennate muscle is obviously much stronger and has a higher peak force, because we know PCSA is related to peak force, so we could just substitute here F peak for each of these muscles. So for here is the strap and the pennate, and then the bipennate muscles here, right? And we could see this one is obviously winning. So we could also ask the question, how is this muscle fiber arrangement affecting length and then peak velocity? So let's look here, and that we can and compare the muscle fiber lengths in each muscle arrangement. Well, this is the kind of the fiber lengths are running from in origin to insertion, and so this would be the length of a muscle fiber. Okay, and then here they're running, you know, here this length. So the muscle fiber length here would be this length, and then here they're really short. They're just running from here to here, so that's the length of a muscle fiber. All right, so clearly the muscle fiber lengths are shortest for the bipinnate muscle and longest for this kind of strap arrangement. And so we could then now relate this to the concept of sarcomeres in parallel row series. We can say, well, which of these muscles has the most amount of sarcomeres in series? And clearly, to have a muscle fiber be this long, I have to have a lot of sarcomeres in series to create that fiber. And so the most sarcomeres in series are going to be for the strap muscle as compared to the bipinnate muscle. So if we think of that, then we can kind of say, okay, well then here the change in length of a strap muscle is much greater than the potential change in length of a pennate muscle, and that's much greater than the change in length of a bipinnate muscle, right? And so what we could see then again is if we think about this in terms of time, and we have the same increment or interval in time, we divide this by time, right? We could also make the case that the peak contraction velocity, okay, is greater for a strap versus a pennate versus a bipinnate muscle. All right, and so what we're learning here is that the basic, kind of ability of a muscle to create force and its peak contraction velocity is partly controlled by how the fibers are arranged relative to each other. Okay, so let's put this all together and see how this influences force length and force velocity relationships. So let's first make a chart of the different muscles, the strap, pennate, bipennate muscles, and put down here how that relates to their peak force, peak velocity of contraction, and overall length. And so essentially the highest peak force came from the bipinnate muscle, so we'll put 1 for that. Came in second was the pennate, and then last was the third, okay, because they're physiologic cross-sectional areas. And the peak velocity of contraction came from the strap muscle, so that was first, pennate was second, bipinnate was third, and it was the same for length. The longest muscle was the strap, okay, and the second was the pennate, and third was the bipinnate muscle. So how does this relate to their force-length relationships? Well, here, the overall length of the muscle tells us the potential for the muscle to operate over a different range of motion or length. And so if we wanted to plot the strap muscle, we'll put it in red. We might kind of start off by giving it kind of a low peak force, which would be there, and then making its force relationship kind of operate over a fairly long range of motion. Okay, and then we could put in let's go right to the bipinnate muscle. Well, it's going to be the shortest operating range, but the highest force. So let's put it really high, but make its overall ability to operate over changes in length really small. So we draw something like this, and then essentially we would put the pennate muscle in between there. So it might be something like this here, where we had its operating length was shorter, and then its peak force was less. So essentially we have blue is the pennate, and the red is the strap, and then the green is the bipinnate muscle. and that's what their relative force length curves would look like. Okay, so if we did the same thing for force velocity, we could start here with the strap again, which is in red. So now it's going to have the biggest peak velocity or fastest of the three muscles, but it's also going to produce what? The lowest peak force. So we could come down here, we go directly over, that was our peak force, so it's going to be the same for both the force length and force velocity, but it's going to go really fast, so it's going to be out here. So my force velocity relationship for the strap looks something like that. Okay, so then for the bipennates, let's go to the highest peak force but absolutely slowest, so we're way up here, right, because it's so, but it has very short fibers, so it really can't produce much velocity, so we're going to make it go right down to zero. And that's the bipennate muscles, peak contraction velocity and peak force output. And then the pennate muscle is going to look something like this. So its peak force is here. It's going to go to something like that. So that's a pennate muscle. So what we're learning is that not only does the fiber arrangement kind of govern that how the muscles perform, it influences their abilities to create high contraction velocities and operate over different ranges of motion when people move. So here let's look at these two muscles, the infraspinatus and trapezius. So the central tendon or origin insertion force in the muscle is directed into external rotation for the glenohumeral joint, and the muscle fibers are running in a bipennate relationship with that central tendon. So this is a bipennate muscle. And as such, we know that given its size, its peak force would be surprisingly high. So it would have a high peak force. It's designed to maximize the peak force output. Now, if we look at the muscle fiber lengths, the muscle fiber lengths here are really small in comparison to the whole length of the muscle. So here's the whole muscle length. And so the length of the muscle fiber with respect to the length of the muscle is low, right? And so essentially it means this muscle's change in length will be small, which means it can only operate over small ranges of motion. And also its peak contraction velocity will also be low, right? Now, if we look at this muscle to the right, the trapezius muscle here, we can see a muscle fiber is running like this. And so this muscle fiber is actually the same as the length of the muscle. So the muscle's running, this lower trap is running the same distance except for the tendon. So the length of the muscle fiber relative to the muscle length is nearly 1, right? And so it's going to have an ability to have a very high change in length. So the overall length of the muscle, change in length of the muscle is really high. And therefore its peak contraction velocity is also going to be high. And then its ability to generate force is really directly, in this case, it's directly proportional to its perpendicular cross-sectional area. So its physiologic cross-sectional area, which would be this kind of cross-section here. So the PCSA that you can imagine in this case is going to equal its peak force. So what becomes evident then is that sometimes we can look at a muscle and just judge by its girth, what its force capacity is. And other times, like for example, the infraspinatus muscle or another muscle that's bipennate or multipennate, just looking at it doesn't give us a very good assessment of its peak force or its peak capacity unless we also take into account its Panasian arrangement. So because of the relative importance of understanding the performance of a muscle for different applications in sports medicine and surgery and physical therapy, people have sought to kind of describe each muscle's characteristics. And so a chart like this allows us to compare muscles. And so here we see the PCSA, the different muscles. It's labeled cross-sectional area, but in the heading, it's actually its physiologic cross-sectional area. And then here's the fiber length. And we can just start looking at this and note different things about muscles. And we can see here's the peroneus tertius muscle here, peroneus teres muscles, it's also called. It has a very small fiber lengths, but a high PCSA. So this muscle here we would know would operate at very low peak velocities, but compared to these other muscles would have higher peak force. And then we could pick another muscle over here, the extensor carpi radialis longus, and we could look at that and say, well, geez, it has a very long fiber length. And so this muscle here we would know creates very high peak velocities, yet in comparison to the peroneus teres, or the pronator teres, has very low peak force. So a chart like this allows us to apply these principles across muscles very precisely. So we've answered that burning question, why do muscles look different, and how it affects their contractile profile. Hopefully this helps you going forward in therapy and anatomy.